Next, welcome Sarah Berry, the Homer Burnell Career Development Professor, MIT Faculty of Artificial Intelligence and Decision Making. Sarah, por favor.
Good morning, everyone. Daniela is a hard act to follow. But I think we were just talking right before the talks. And one thing I think is really interesting is that we're kind of coming from two opposite ends of this pretty broad sector, right? We have Daniela working on the ground with indigenous communities in remote areas, and I'm at MIT, where we're trying to, build maybe like the future of technologically advanced systems. So I think one thing that's interesting is, despite the fact that we're coming at this from very, very different pieces of the puzzle, we both have this strong focus in the message we wanted to communicate around making things useful. I got my start in this space a while ago, back in 2012. And this was before machine learning worked, right? My very first research project was freshman year in undergrad, and I was working with Panthera to try to use artificial intelligence to identify individual snow leopards. And this was back in the day where everything was super handcrafted. I was building these mathematical algorithms to find every spot and calculate their mathematical curvature using wavelets, and then do astronomical pattern recognition plus the curvature features to try to get the same spot pattern in a new picture. And it worked some of the time when the photo was perfect, right? And then the snow leopard would get wet, and the pattern changed, and it was totally trash. But the thing was, even though this was something that was really hard to get to work, and the tools weren't there yet, and honestly, we actually still haven't solved automated snow leopard re-identification because this is just a really hard problem, I got hooked. I could see into the future and see that these technologies were advancing, and that they were going to fundamentally change the way that we monitor and study life on Earth. And so I was like, this is what I want to do. I want to build computer vision technology, artificial intelligence technology, to help us monitor wildlife and species. And I've stubbornly continued to try to do that, and now that's what I do with my group at MIT. We focus on trying to understand what machine learning can do now, what are the gaps that are relevant to these biodiversity problems, and how do we actually build solutions that help us address the things that matter? So for us, that can look like trying to build better algorithms that can robustly identify things that are rare, things that are visually similar, and even find novel categories like new species. These are things that are not easy for current machine learning models. We also focus on how we build systems that adapt well to new environments, new tasks, without needing too much effort and computational resources to get them to work. Important when you need things to work just as well in North America as they work in Lima or out in the remote Amazon. And finally, and increasingly, we're thinking about how we build systems that share information across all of these different heterogeneous data types we're collecting. Help us reason across the information we have, filling data gaps and knowledge gaps, and trying to support scientific discovery or just understanding of trends. Now, I do think, just to set the stage for this talk, AI is something that has gone through kind of different cycles of understanding in the broader public. And I would say in recent years, everybody knows what AI is, but they all have a very specific idea of what AI is. And it's basically AI is ChatGPT, right? And I actually think that really important and relevant to this community is just this reminder that AI is a really vague, broad umbrella term for a huge set of methods, some of which are large-scale, generative, autoregressive, predictive models like ChatGPT, and some of them are designed to be small, efficient, carbon, resource useful by design. And I think it's important also, when we're sort of thinking about this sector and the things that we care about, to think carefully about how we use the tools that are available. So I'm not here to tell you we shouldn't be using ChatGPT, but more just to remember that when people say AI, it doesn't just mean one thing. And so what I do want to point out, and this actually, it was nice, you set the stage. This model got brought up in the first talk. It's something that's being used in the remote Amazon. AI is really good at speeding us up. When we carefully design AI models, what they do really well is help us do easy things fast. So like that snow leopard problem I brought up. Still hard. We still can't do it because it's hard for humans. But things that are pretty easy for humans, like is this an animal? We can do that really fast. And the ability to do it fast and the ability to do it robustly makes it useful. So this model now gets used by thousands of organizations around the world. For example, the Idaho Department of Fish and Game, is collecting 11, now closer to 20 million images a year. And then they build human review systems, and they check a much smaller percentage of those before they make decisions. So AI is useful, right? We've seen AI be useful in this sector. But let's just think a little bit about how we use AI and what the kind of space of useful looks like. And I do want to point out, like in theory, or at least what we were sold coming in, is you would like, and specifically I'm talking about these predictive models, things like species identification models, feed-forward prediction, land cover prediction, crop type prediction. So in theory, you're going to collect data. You're going to run that data through a model, and that model will give you the predictions. And then you're going to do analysis on the predictions you get from the model. Now, we've learned as a community very early on that this wasn't sufficient, right? Because machine learning models aren't perfect. They make mistakes. So actually, in practice, it looks a little bit more like this. We collect data. We run the data through a model. We correct the outputs, right? We do some sort of going and verifying and checking and doing some correction. And then we use that corrected data to do our analysis. But then also, what we usually find out is that like the corrected outputs, well, we find out that the model wasn't working as well as we wanted. And so we've spent a huge amount of time and resources in this community focusing on this piece of the problem, on trying to make us use AI and help AI make us go faster by correcting outputs, using those corrections to retrain models, and trying to get machine learning models that are closer and closer and closer to perfect, with the idea that as the models get better, it's going to save us more time. Now, I think that we're getting pretty good at this. All of the investment of time and creativity and talent of the people in this room is making this process start to work better and better. And not only do we have the methods for it, we actually have the infrastructure and the tools for it, right? There are so many different platforms that people are building that help us do this part. But I think we're really wasting time because it turns out that this is also an option, right? We can think about designing methods and systems where we're correcting our outputs not to try to get a perfect model that will label every single data point correctly, or a system to correct the outputs of a model so that you get every single data point labeled correctly. And instead, we can think really carefully about how we can choose strategically what to correct to make sure that we're improving our actual output, our understanding, and our trends. And so no model is perfect, right? If you go from a model that is 50% accurate to a model that is 80% accurate, or choose your own machine learning metric, yeah, that model will probably save you a lot more time. If you go from a model that's 90% accurate to 95% accurate, your mileage may vary. Like in terms of how much you can actually trust that model, how much time it's actually saving you, it's diminishing returns, right? And actually, I think what's important is we're missing this piece of the puzzle. The ways that AI can be unreliable can actually be really specifically ways that impact our analyses downstream. It impacts our ability to get the correct ecological estimates that we care about. This is an example from individual re-identification. All right, so in the first picture, we have a known individual, links A, and then we get new data. And the picture on the bottom, links B, that photo is nearly identical to the first one, right? From a perceptual perspective, far away, that looks really similar. Machine learning models are really good at saying these two things are similar. We want them to be good at saying, like, these two links are identical, but they're going to get confused when you have all of these other confounding factors of similarity that are not just the animal itself. And it's not just the environment, it's the pose, it's the lighting. Whereas you might have another picture of that same lynx, now in a very different environment, different context, it's black and white instead of color, and all of a sudden, that's actually also hard in a different way. And now we know that this is true, right? Like we know it's not necessarily easy to get these models to be perfect, but what matters here is that if we identify these two as different individuals, well, now we've accidentally said there's more individuals in the population, so we might have an inflated abundance of a rare species. We might underestimate the home range of this species. Those are things that actually matter when we're trying to make decisions. Same thing if you accidentally merge two individuals that are different into the same one. You might overestimate the movement. You might get a distorted social network. You might inflate survival. So I want us to think more carefully as ecologists about how we use machine learning models and try to think about how we can actually do correction that influences our understanding of the system instead of trying to get every single prediction to be correct. So instead of actually correcting for improvement of models or correcting to label everything correctly, we can correct to calibrate, for example. So one of the projects that we have is we've been working on the East Coast with herring populations, on the West Coast with salmon populations, and we're basically just trying to count the escapement of these species. How many fish have made it upstream to recruit, breed, to come back in the future? It is really hard to count fish when they're running. There's a lot of them, they're overlapping, it's a really difficult problem. We cannot get the models to do this correctly in a reliable way, right? I actually don't believe that we're going to ever get a model that will perfectly count all of these fish. We can't get humans to do it either. But what we can do is we can train models to do their best, and then we can design systems that use the predictions of those models as a prior, as important sampling, and then you actually go in and you manually correct strategically so that you can get an unbiased estimate of the true count. So instead of spending a lot of time, thousands of hours, trying to get the model to count every fish, you just say, I have a model that will help speed us up, and what I care about is an unbiased estimate of the total recruitment of the population. Now, I think quite importantly here, because you get an estimate with uncertainty, you can actually justify this in legal systems. Unlike my model gave me this predictive ladle, and I wasn't able to check everything, or I had to go check every single thing, which then it's not really saving you so much time. This gives you something that you can actually kind of litigate, which becomes important when you're talking about fisheries in the American West, where every single count that you come up with is going to be fought by someone. Now, you can also think about systems where instead of trying to correct to calibrate, you can actually just strategically verify evidence and generate a system where all of the actual evidence is human-checked. So let's think about what this looks like. In the earlier talk, she was talking about abundance estimation. Abundance is our occupancy estimation. So occupancy is a case where the types of errors really matter. If you predict a false positive, if you predict an animal was there when it wasn't, the statistics break. That is breaking the assumption of the underlying model. But if you just miss an animal when it was there, well, we already have the idea that we have an imperfect observer. Now our machine learning model is also an imperfect observer. It might not always see it when it's there. Now, what's impossible to do is guarantee your model will not generate a false positive. But if you know you're going to look at the occupancy, summer and winter per site of a species, all you have to do is you go check. In the summer, you rank them by your probability of that animal. You find a single one that you can verify, and now you know it was occupied, verified by a human. And then you design a study where you say, I'm going to look through 100 or 1,000 for all those sites where it's not. And if you go through, that's your effort. And now you have something where you can get a directly verified occupancy estimate without actually spending nearly as much time as you would spend to try to get a model to predict every single animal correctly. Because after you've found one, you don't care about the rest. You know the site was occupied by that species. And of course, that's just one type of ecological model, but we can think about designing similar systems for many of the things that we actually care to measure. So I think, and we need to think a lot more as this technological community about this idea of correction for analysis. Think about things that make this statistically robust. Think about stuff that makes it much more efficient. You know, I'm talking about labeling 5% and getting a robust estimate instead of labeling almost everything. And specifically, what this is doing is it's shifting the focus from like AI to ecology, right? It's saying, like, we don't want to focus on machine learning metrics, per data point metrics. The performance that matters to us is the performance that influences our ecological trends. It influences our understanding of the system. And then I just also want to say that this is also where, when we start to bring in these generative AI models, it gets hard, because generative machine learning is not, it's stochastic. If you ask it the same question twice, it will give you different answers. There are methods that we have tried to build in the AI community to come up with consistency, and they usually rely on asking the model the same question 10 or 20 times and taking a majority vote. When we're talking about computational efficiency in this community and how important that is to us, clearly that is just far beyond the scope of what is reasonable. So we can do this, but we need to be careful. So I think the point I'm trying to get across here is that we've really figured out how to build systems that try to improve our prediction. But I want us to change our focus going forward to how we improve our ecological monitoring on the ground. And I think that this actually really requires us to do things that are much more interdisciplinary, because AI researchers are bad at statistics. Like, they don't know about ecological models. They don't know about the assumptions of what you're going to use downstream. So we need actually to build these skills and these systems together. And this is one of the things that we do in this program that I've run. We just finished the 4th iteration of it at the Smithsonian Conservation Biology Institute, where we're trying to just teach ecologists to build the machine learning models, but also the ecological systems around them, so they can get to measure what they actually care about efficiently. Yeah, so thank you very much. And if you do want to continue the conversation on the method side, we have a Slack channel called the AI for Conservation Slack that's a really open and great community for this. Thanks, guys.